Regarding the range itself, today we have a standardized range between 1,500 cubic meter per hour up to 16,800 cubic meter per hour. But what you need to keep in mind is that a DW package, DW machine, it's only an adaptation of another series of machine. So we could have a 50 cubic meter per hour machine running at with water injection, but that not really works because the water injection system and everything are really costly compared to the cost of this small machine. And we can go up to a 60,000 cubic meter per hour machine. That is our biggest blower existing. But today the market is more moving on the turbo blowers for this kind of solutions, as you can you saw it in the map technology. So this is where we are really strong, really efficient, especially if we can focus a little bit between the 43 and the 110, a little bit on the 170. Vacuum level, we can reach 400 millibar with single stage, 50 millibar absolute, and 150 in double stage for sugar industry. Water injection, we are talking about liters per hour. So the maximum is 1.3 cubic meter per hour, and the minimum is 100. All those figures that you can see here in the table are the maximum consumption. That means that any DW90 could be running with a 600 liter per hour water consumption, and with an installed power of 90 kilowatt, for example, instead of the 160. We are only stating the maximum that we can do with that. In terms of options, we discussed about, I mentioned the frequency converter and control panel. The electrical cabinet, and especially the frequency converter, is a must to have with a blower machine. Why? Because the blower machine is a volumetric machine. So that means when you decrease the speed by 10%, the power consumed is directly proportional. So that means 10% saved. We will see a little bit later what can be this impact on the VFD, thanks to this following the needs of the production and so on. But that's really powerful, and that's why we integrate it into our into those packages. We have also an internal coating. So depending the application, obviously, starting with a heat treatment, that is the basis of the basis, up to a chemical nickel coating that is answering, let's say, 80–90% of the applications that we are facing with chemical coming inside the machine. And in the end, inlet filtration to provide a higher lifetime for the machine for certain applications when we have higher level of particles, minerals, or this kind of stuff. What do you need to keep in mind with those DW packages? In terms of efficiency for a single stage, that is clearly one of the best in class when we are above 400 millibar absolute. It's clearly reliable and robust. We have for proof that our machine are running for 60 years now. So that is the best proof that we can have. This is something that is stable along the time. We don't have any influence coming from utility. Liquid ring pump, if you have a higher temperature on the sealing liquid, it will create a drop in your efficiency. That's not the case for a blower. Even if you have a 60-degree water inside, no problem, that will still running. So that's clearly stable and will transform the vacuum level into something that is a parameter you can control instead of just having it and really don't know how to move it. Completely oil-free, so no contact between the compression room, not compression room, but with the inside of the machine with oil. The only oil present is for bearings lubrication, changing once per year. And in terms of maintenance, this is a really low cost because, as discussed, just say before, really a small amount of maintenance, oil, maximum 15 liters, 20 liters of oil per year. One synchronous belt for the transmission with belts, and a cartridge if you have a filter, and that's all yearly. So now we go on the case studies, and should be certainly more interesting and more real and actual. So regarding the molded fiber, we made this case study because we are a partner who are required our analysis on the current situation. This user has several machine oil screw vacuum pumps, and he wanted to do an extension on that. We just checked what will be the parameters once the extension is done, and also declining to put our machine on top of other technology, because as you can see, the vacuum level requested is 300 millibar absolute, and the machine itself is running at 250 millibar absolute. That means we could have a trouble having DW packages at 300 millibar and vacuum pumps at 250. That will create some discrepancies and perturbation along the pipe. So we completely declined. However, what it did is that we made some kind of case study with them and working on what we could do instead of that. What would be the best solution from our point of view and experience and return of experience? Because molded fiber is something that we know very well. So what we did is that we just said, okay, we took the parameters, flow requested 15,000 cubic meter per hour, vacuum level 300 millibar absolute, so minus 700 millibar gauge. And what we did is that we did what we call a double network. So it's like a double stage system, but with several machines. So if you go from the production lines and you follow the blue arrow, going through the filtration just to avoid any kind of trouble, you arrive in two machines that are DW90, 7,500 cubic meter per hour each, so the 15,000 are reached. Each machine have a power absorbed of 68 kilowatts, with a machine speed around 1,500 RPM. So direct should be really perfect. And we have a delta P, so delta pressure between inlet and outlet that is a 250 millibar, so really low delta pressure, because we are just using those machines to handle the flow. And thanks to the compression ratio, we are decreasing the flow at outlet. So we can just put one machine, the W90, 8,100 cubic meter per hour, instead of a lot more, with a power absorbed of 125 kilowatt, because this machine at inlet is 550 millibar absolute, and will go at outlet to the atmospheric pressure. By doing that, we are achieving a complete absorbed power for this centralized system of 261 kilowatt. That is clearly more than half what the customer already have today. And this is why we are working on this case study, because there's clearly a big impact, as you can imagine, on the savings. So I know that you are people who are attending now or coming from different countries with different price of electricity. So we just fixed a price of 15 cents. That is quite common, I would say, today in Europe, for example, with 8,400 hours per year, because this is a 50 weeks of running with 2 weeks of stop. That is most of the time the case for molded fiber. We're talking about nearly €500,000 saved per year just by doing that, just by having the right solution. Would be even higher, obviously, with the energy crisis that we are facing today. And some countries are facing more, up on 20, up on 25, or even up on €3 per kilowatt. So clearly, that's really important. Another case study is on the papercraft production. So here we replaced the liquid ring pump that the customer already had before by two DW90, also operating both with a VFD at 60% nominal. And we achieved 83 kilowatt power consumption instead of 220 kilowatts. Yearly, we are talking about 1,150 megawatt hour saved, meaning 345k euro around for the same fixed price. I went quite fast on the last one because I see time is running and I don't want to don't want to be late. We will go on the optimization, and here we will go a little bit more in detail and on the physical principle and formulas. So the first point is the vacuum flow relation. On the dewatering application, what we monitor, why we use vacuum system for that? It's to remove a certain mass of water from the product. That's all. The vacuum level, it's a drop in air density. That means the higher vacuum level you have, the less density you have, so the less molecule. That means if you want a constant mass flow, that means always the same mass of water removed per hour with a higher vacuum level, you need a higher volumetric flow. That's just a physical principle. So that's why I just write it down. The formula, I think most of you should certainly be aware of PV again, is equal to NRT. I will not teach you anything on that. Just by using Marion-Boyd's equation formula, we have P1 V1 is equal to P2 V2. At the time for this specific application of this formula is the same because we are on the same in the same conditions. We can transform the volume into a flow. That means P1 F1 is equal to P2 F2 with some, let's say, slight tolerance. We know that it's forgetting some points, but it's giving really a 95-98% accurate flow. So let's take an actual example. If you have a 7,500 cubic meter requested at 550 millibar absolute, what would be the flow required? So just replacing P1 F1, P2, F2, and we have F2 that is around 10,300 cubic meter per hour. That means that for the same mass flow, so the same job basically, the same mass of water removed, just by dropping the vacuum level by 150 millibar absolute, that increasing by 25% the flow you request in volumetric flow. And obviously, if you need 10,000 cubic meter per hour, you will need a machine to do that. So we need a size of machine with the consumption that is going along. So that's an increase of power consumed. And that's one of the main points that we are working on, is to find what is the real vacuum level that you need. It's not obviously what you already use. Most of the time, we are working with and learning all together to fine-tune this vacuum level and find the best one, keeping a little bit of margin of security. That's completely normal due to the pressure drop that we'll see just after. But having too much vacuum is not a good thing. I really often hear about something like, the more I have, the best it is. That's not true for the vacuum. That's a complete opposite. The more vacuum you have, the more flow you need. So that's completely counterproductive with the efficiency. So that's really one big point, because you can imagine that 150 millibar is 25% more. Imagine if you have 300 millibar or this kind of stuff, and it happens. Regarding now pressure drop, that's another point, and this is also one of our support in Hibon. That helps to know the actual parameters between the vacuum pump and the production. That means if the production requires 500 millibar absolute, but you have a vacuum pump that is running at 350, you have something wrong somewhere. So that's also important to understand what's going on between the vacuum production, the vacuum pumps, and your production line. We can calculate those when we can estimate those pressure drop along piping by combining the straight pipe and what we call the specific points that are creating pressure drop. So here you have, sorry for the French part, the formulas for different kind of single specific point, depending if it's reduction, silencer, turn, more or less aggressive turn, this kind of stuff. That will help us to estimate if the piping today is good or not. And that's really important. That will also optimize the power consumption linked to the vacuum system. And obviously avoid increasing the flow to compensate the higher vacuum level. Why do I say that it's avoiding to compensate the higher flow requested? It's because the formula we just saw before, P1F1 is equal to P2F2. It's also something that you can apply when you have pressure drop. So another actual example, we will keep the same flow, same vacuum level. We will take 70 meters of piping length and two cases, one DN250, one DN400. The formula that you can see is, let's say, the formula used for pressure drop calculation using Darcy friction coefficient and also Reynolds number, depending the velocity, so the speed of the air inside the piping multiplied by the molecular weight of the fluid, so here some air, and with length and diameter. The first calculation, the first point that we will see that the flow, in fact, will be 8,418 cubic meter per hour. Because when we are doing the calculation, we have an airspeed at 47 meter per second. It's not cubic meters, sorry, it's my mistake. We have a pressure drop total that is 55 millibar. 75 millibar. That means for the same job, once again, for the same mass flow, we need to increase the flow to 8,400, and we have a power absorbed that is 150 kilowatts. If we go now on the DN400, we have a slight difference now with the requested flow initially, because we have a pressure drop that is 8 millibar, so much more interesting. And the airspeed is 16.7 meters per second, and the power absorbed is 115 kilowatts. So you can see that for the same machine, for the same job, just by changing the diameter, we have a big impact on the power consumption. Only by changing and by, let's say, choosing the right diameter, you can save, on this actual example, nearly 300 megawatt hour per year and almost 200 tons of CO2. So in terms of sustainability and CO2 footprint reduction, only the piping itself is really important. And that's why in Hibon, in gas-around, we are having a big picture. We are not just having a look on the technology itself. The complete picture is important because we need to know what will be the environment our machine will run and giving support on that. Last point on the optimization will be regarding the VFD itself. So let's focus the first curve that you are seeing. It's a fixed flow at 10,000 cubic meters per hour. This is the vacuum pump that you can find in any case. The blue curve, this is the production need that is changing because for several events, and we'll see that. I just took the application of pulp and paper market for you to understand. This is the power, the fixed power, because there is no change. The machine is always giving the same performances, same vacuum level, and nothing change. And here is when we are doing with the frequency converter. So what happened? When we have I'm focusing on the felt, on the pulp and paper machine. So when you have a new felt, there is nothing stopping the air crossing the felt. So you have like a big leakage on atmospheric air. So you need a real big amount of flow, and you need to design the vacuum pumps and the vacuum system to be able to handle that. Because if you don't, you will lose some production capacity. But after a certain time, between 3, 6, 7 days, the felt itself will be completely clogged, or not completely, but will be clogged by the fibers, the pulp inside the felt. At this moment, the resistance on the felt is really stronger than when it's completely new. So it's much more easier to have the vacuum level achieved by the vacuum pump. The problem is that if you don't have any frequency converter, it will just continue to produce the same flow as designed for when the felt is new. When you have the machine with the frequency converter, you can decrease at this moment. On the we can see on the curve that it's going a little bit up. Why it's going a little bit up? Because you can have a change of product. So I know it's not happening every day or not every 3 days or something like that. But in any case, when you need a change of product, you will have, depending the weight of the product, the speed of the machine, and all those parameters, the vacuum flow and the vacuum level are not exactly the same. So that the need will go up, and the machine will follow that. So we will have a certain moment of the machine when the machine will have this higher flow, not the maximum one, but nevertheless, and another change of product going back to the original, let's say, clogged situation. What you can see here is that you have savings, not even linked. I'm not even talking about technology, not even talking about pressure drop, not talking about vacuum flow, just following the need thanks to the VFD, because of the machine is proportional. The machine is volumetric, so the speed of the machine is proportional to the power. You have a difference in power from 255 kilowatt to 185 kilowatt. So 60 kilowatt, just because of the frequency converter. That means a lot, really a lot of power saved just because of using a frequency converter. And this is the end of this webinar. I hope it was clear what I explained. If you have any questions, please feel free to ask them in the Q&A chat box that you have available to ask us to your questions, and I will gladly answer any question that you have. I think. Yeah, you will have video of this presentation. In fact, the webinar, the complete webinar will be sent, if I'm not mistaken. Could you repeat the benefits of water injection? The water injection are three main benefits. That is the efficiency, because the water is, let's say, closing some gaps between the rotors, avoiding some air going the wrong way. So when you have a revolution on this way, you always have a little bit of air going on the wrong way. So if you close the gaps with water, the air can't go on the wrong way. So that means less leakages, mean better efficiency. And on top of that, it's cleaning the inside continuously to avoid paper, pulp, sugar, any kind of stuff staying inside the machine, and decreasing the temperature. That's why we're also able to have a higher vacuum level. Thank you, Daria. Thanks a lot. The inlet filtration for the PD blowers require, it depends the kind of filtration. It also depends let's say, the really accurate application. Depending the particle that we can see, we can adapt, or it will be a polyester cartridge, really something simple. And when we want to avoid having too much clogging cartridge, we can go on something that is slightly bigger, because we have quite tolerance on the DW packages machine in terms of size of particles. We can have a 25 microns up to 40 microns for the biggest machine particles going through. And in this case, we can use a stainless steel element that is never clogging. In fact, you can even use some water system to clean it continuously or by cycle, depending what you want. So we can do something different on that. Do you need? No, we don't have. The only point on the water that we are targeting, it's not we don't need a perfect water, not completely fresh, not completely clean. Just the only point that we are targeting the hardness to avoid having that too much calcium in the between the rotors. And another point on the hardness, it's when we have a water that is a little bit too hard, what we will do is that we will decrease the temperature of the outlet. What does that mean? When we install the package, we also change the flow of the water injection by monitoring the temperature at outlet. We know that when we are up to above 70 degrees at outlet, we have a risk of creating calcium inside the machine. So we will go to 50 degrees, or if we can achieve 40 degrees. So depending the hardness, we can also change that point. Thank you, thank you, Martin. Is there any other people having some questions about your application, the products, the different thing that we can, the flexibility, technical flexibility that we can have? So in this case, I would just go on the last slide. I really do thank you for your attention during this webinar. That was our first one in Hibon, and we are really pleased to share this moment with you. Thank you for your attention. Thank you for your questions. Really important for us. For the application, sugar, paper, you can add mining even if it's not really on the trend. But oil and gas is not with dewatering application. It would be more with other product manufactured by Hibon. If you have any question, you have my contact here. Don't hesitate to feel free to come back to me, and I can give you more detail about oil and gas product that we have available. So I was saying thank you for your attention. Thank you for your commitment, because I know that being here right now talking about savings, it's the right way to find the solutions to solve the issues we are facing. As I said, don't hesitate to send me your question if you have later some other question, if you want to have some studies about your own application and what we could achieve. That's something that we will gladly support you to do. Okay. Thank you for your attention. Thank you, everyone. And I think we can close the webinar now. Feel free to write down my contact and come back to me if you have any question. Thank you very much. Have a nice day. Bye-bye.